Hello everyone, welcome to the Spintangle. Today, in this lecture 8 of Statistical Mechanics, we will be discussing on Ensemble Theory of Statistical Mechanics. So, let's start. Ensemble Theory of Statistical Mechanics is a very important theory in dealing with statistical systems. Please let me write it first. Ensemble theory, we know a statistical system is which that has large number of very large number. I'm writing this clearly that very large number of constituents. Means a system having a large number of molecules, a large number of atoms, large number of particles, whatever it is, will be treated by statistical mechanics. So to treat it by statistical mechanics, we need to know about what is ensemble theory. Okay, this ensemble theory is nothing but this is a let me change the ink first. Let me write some point about this ensemble theory. It is a mathematical tool to study statistical systems. Okay, what we use in case of ensemble, what are the ensemble? Okay, first of all, in case of ensemble we use a system. Say this is a system. Okay, this system, say this system has a number of particles. This is n is number of particle. System has a certain volume, system has a certain energy. Okay, and then we make its copy. These are called mental copies. Say the system. So if the mental copy of the initial system, this is the initial system. Say this is initial system, and the second one, this one is the mental copy of this system, of the initial system. That means it has to contain n number of particles and has to maintain a volume v, and its energy is E. Because it is a copy, you can relate like this, that if you are going to Xerox a particular you are going to Xerox a particular paper, in which what you can do, you can put the paper on a Xerox machine, and how much you need does not matter. You can copy it 100 times, you can copy it 200 times, you can copy it 400 times. Okay, these are the copies. These are not actually these are mental copies called, because these are only by our thought process. Okay, these are the copies. These are the copies. Why the necessity of copy? Okay, why the necessity of, and so on, in a large number, in a lakhs or crores number. Okay, you can make its copy, and this makes the system. This makes the system ultimately. Okay, what is the necessity of these kind of making these kind of mental copies? Say you are changing this system by putting an extra change. Say this is the change. This is the change on the initial system. Then when you will take the copies, then the change will be produced on each copy. Okay, say you have a paper, this is the original paper, this is the, I'm writing it initial, this is the original paper which has NVE as a energy, and these are the copies. If the initial or if the original paper containing a black spot, say this is I'm just this is just a contradiction. Okay, initial copy has a black spot on its on its surface. Okay, then it will be produced and also reproduced on its mental copies. Okay, these are the Xerox copies, you can say. These are the Xerox copies. This is how a statistical system is treated. If you make a change slightly in the very initial system, then the change will be introduced on each of its mental copies. Okay, this is what we call the ensemble theory, or sometimes it called ensemble theory. Okay, you need to pronounce ensemble first. Sometimes I used to call it ensemble, sometimes it is called as pronouncing is ensemble. This I think this is, you can check it on Google. Okay, ensemble is the right way to pronounce this thing. Okay, so now write a point in ensemble theory. We consider an ensemble means nothing, ensemble means a collection. Okay, a collection or a group of an ensemble that is a collection of large number of mental copies. What you call mental copies. Okay, large number of mental copies of original system. That are microscopically identical means looks like same. Okay, identical but are different macroscopically. Why this is different? Why this is macroscopically different? Scopically. Why this is macroscopic? Please read the comment. That in ensemble theory we consider an ensemble that is a collection of large number of mental copies of original system. I have discussed this thing earlier, but the extra line is produced here is that are microscopically identical but are different macroscopically. What does it mean macroscopically? We know what are microstates. Microstates are the I have written it earlier. Microstates are the possible internal arrangements. Okay, internal arrangements of the constituent particles. This means if you are looking through this fact that this system, this is the, say this is the original system. Okay, this is the original system. In the original system there are four number of particles, say four number of particles, energy E and volume V. I am writing just for a general purpose. Okay, so these are the four number of particles. Say these are the four number of particles in the original system. That means what you can do from this thing, that whenever you will take the mental copy, it is not usually possible to take the mental copy of a thermodynamic system, because this thing goes through this thing, and whenever you are making this thing copied, the particle can rearrange in another way. But this you can see this thing also four number of particles. Okay, in this thing also there are four number of particles. Also this the total energy of the system is E and V, and volume is also V. But you can see easily that the internal arrangement of the original system and internal arrangement of the copy goes disturbed, and whenever you are taking another copy, this also contains four number of particles but in a different manner. Say this particle goes here, this particle goes here, this particle goes here. Okay, this is also has a different internal arrangement, and what we can see the possible internal arrangements goes a change, and this makes the macro state a different macro state. Okay, am I correct? If you have any doubt about this, if you have any query about this, then you can comment. Okay, you can comment. I used to try to solve your each and every comment. Okay, these are, you can see these are different microstates. This is microstate 1, say this is microstate 2. Okay, you are taking just copy, but the copy, it is not possible to take a copy like Xerox copy. In a Xerox paper, say the A letter is written here, and whenever you are taking a copy of this paper, the A letter remains in the same position. But in case of thermodynamics, in case of statistical mechanics, as there is a term called entropy, the entropy makes this. The entropy is the degree of disorderedness. I have told it earlier in the lecture of entropy. Entropy makes the system disordered. Okay, this means the microstate goes a slight change. Okay, because of the entropy, this thing will not remain in the same position. Okay, okay, so this was the ensemble theory. You can read it from any book. Okay, now now going to the mathematical part. What is the mathematical part? The previous discussions were about the theory, the completely conceptual discussion, but now we have to deal with the mathematical parts. Okay, what is the mathematical approach in dealing with ensemble theory? To know about ensemble theory, we have to deal with one thing. This is called phase space. It's called what? Phase space. Let me write it. A very important topic. Okay, it's called phases. Okay. What is a phase space? What is a phase space? Now we have to know about this thing. What is a phase space? Let me write it clearly. Phase space is nothing but the position and momentum space. Okay. Wait for a while. It is the position and momentum space. Okay, so it is sometimes written as position by Q and momentum by P. Position has three components, that three dimensions you can say, and these are x, y, z, x here, y here, z here. This is a right-handed system, and here momentum also has three dimensions. These are called momentum dimensions. Okay, dimensions made by momentum, px, py, and pz. Okay, phase space is further recognized as phase space is further divided as two other space. Okay, these are nothing but the classification of space phase. Phase space, wait, just wait. Okay, phase space is classified by mu space. I will be discussing on mu space and gamma space. Okay, what is mu space? This is single particle phase space. This is single particle phase space. And what is gamma space? It is n particle phase space. Okay, n means what? N means greater than 1. Greater than 1, not one particle. Okay, or this is the, you can write gamma space as this is, it is a collection of mu space. Now going deep into the mu space. What is mu space? Let me change the ink. It is the phase space of a single particle. I have written it, phase space of a single particle. Okay, say in 3D, so I am considering example, I am giving an example. Consider monoatomic particle. Okay, considering monoatomic particle, what we can see from this, the monoatomic particle, say monoatomic particle, I am drawing this, a monoatomic particle. Okay, it can have three positions can have x, y, and z. Also three components of momentum. What are that? Px, Py and Pz. This is called, these are the three spatial dimensions and this is called three momentum dimensions. Therefore, the number of total dimensions become what? The number of total dimensions become 6 dimensions. Okay, this is just a mathematical representation. You have to know about this fact that mathematicians used to do one thing, that they make they can take any dimension anywhere and and use mathematical techniques to deal the system. Okay, this is x, y and z. These are the 6 dimensions. Okay, so what we can call that, for a monoatomic particle, the dimension of mu space is what? Is equals to 6. Okay, generalizing the more I am generalizing the fact, generalizing, this is the ultimate thing. The general formula of this, the general formula is dimensions, or the general formula is dimensions. If you are asked that, say you have a 2 particle system and what is the dimension in mu space? Okay, what is the dimension of this system in mu space? Say the dimension becomes 2 times f. What is f here? F is called degrees of freedom. F is called degrees of freedom. Okay, I will go degrees of freedom on the next lecture. I have to go today, so okay, say I am taking this degrees of freedom. What is degrees of freedom? It is the independent motions, the number you can write it, the number of independent motions of a mechanical system. This is called degrees of freedom. Degrees of freedom. So you can easily check for a monoatomic the degrees of freedom. First of all, you have to understand the degrees of freedom. For monoatomic particle, the degrees of freedom are what? That the particle can go in the can move in the this way. It can move in this way. Okay. Therefore, in the x-axis, the particle can easily move in the x-axis, x and minus x axis. The particle can also move in the, say this is z-axis. Okay, that is z and minus z axis. The particle can also move in the y-axis. The particle can also move in the y-axis. What is y here? Sorry, this is x, this is y here. Y and minus y axis. These are the 3 degrees of freedom. These are the 3 degrees of freedom. Okay, degrees of freedom are can be more classified. You can dig into the more general theory of degrees of freedom, that degrees of freedom had translation degrees of freedom, rotational degrees. I am not going into too deep on the fact. Okay, 3 degrees of freedom. This means f is what? F is 3 here. Okay, therefore dimensions in mu space will be what? I have written it earlier that 2f, therefore it becomes 2 times 3. This means what? 6. Here you can also see this is by formula, this also 6 and this is also 6. Okay, so try to use the formula. Say if you are given a 2-particle system, 2-particle called diatomic, if you are called diatomic, yes, diatomic molecule. Diatomic molecule, say this is a diatomic molecule, sorry, you're not going to the diatomic molecule. Okay, taking monoatomic molecule in 2D, say it will be more interesting. Okay, monoatomic molecule in 2D, in 2 dimensions. Say monoatomic molecule, there is a monoatomic molecule. It is just a mathematical illustration. You cannot take a monoatomic molecule in 2D. Okay, I am just writing it mathematically, just for our mathematical understanding. In 2D, this means there are how many positions? There are xy, there are how many momentums? Px and py, so that you can easily say that the dimensions of mu space becomes what? 2 dimensions from positions, 2 dimensions from momentum. That means 4. You can calculate from this also, and you can calculate from the degrees of freedom formula also. That what is the degrees of freedom formula? That the particle can move in this axis. This means, say this is x axis. Okay, the particle can move in this axis also. Say this is y axis. As this is a 2-dimensional system, there will be no other axis rather than x and y. If you consider this thing in momentum, I am giving this momentum in green color. Okay, say the momentum. Okay, there will be another axis of momentum, there will be another axis of momentum, which are px and py. So the degrees of freedom will be what? Degrees of freedom will be 2, because the particle can move in the spatial x direction and the spatial y direction. The degrees of freedom becomes 2. Therefore dimension in mu space will be what? Dimensions of mu space, from formula, I am writing this thing from formula only. Mu space will be 2 times 2. This means 4. Okay, this is the general concept of dimensions in mu space. Okay, I am giving a homework to do in the comment box. Say monoatomic particle in 1D. Okay, comment on the comment box. Okay, now what is the dimension? I am going to, sorry, I do not have much more time today, so I have to leave this thing up to this. Okay, and I will make a separate video on gamma space. Gamma space will be discussed on the next video. Okay, thank you for staying with us, and we will be talking about atomic physics from next week also. Okay. Okay, so thank you. Like and subscribe and share among your friends. Okay.